Thank you. Thank you for the invitation. So today I start the lecture about tropical Hodge theory. I will do with Omidami. So classical Hodge theory is about complex varieties, and so the question is more or less to which point the tropical cohomology of a tropical variety looks like the cohomology of a complex variety. So it's more or less the question we want to answer. And so today we will see that in some very specific cases there are some complex varieties whose tropicalization verifies that the tropical cohomology of the tropicalization is exactly isomorphic to the complex cohomology of the first variety. So in this case, of course, the tropicalization, its cohomology looks like the cohomology of complex variety. So in fact, so tropical Hodge theory works for, okay, so yes. Okay, now let me start. So I will take K valued field. So I don't know exactly the condition we need for everything to be okay. So I will say, so either K is C with the valuation V such that VA equals 0 if A is different from infinity. Sorry, equals 0 if A is different from 0, or VA equals infinity if A equals 0. So this is the valuation. So here it's a trivial valuation. It's the only natural valuation on C. Or for instance, you can take K to be the field of Puiseux series. And C, introduced by Eric. And so, so a definition for me, the tropical summering T is R union infinity with an additive law and a multiplication law with, so it's what Eric wrote for A, B, and T. A times B equals A plus B, and A plus B equals the minimum of A and B. So I want to insist on the fact that the neutral element here is 0, and here it is plus infinity. Okay, so if I have a polynomial P in K 1 plus n minus 1, etc., then n plus n minus n, plus n minus 1. So I can look at the zero locus ZP, which is which belongs to the, so I write TKN. This is by definition K star to the n, which is the torus for K. And now I can also tropicalize P. And so I define, so if P is of the form, okay, sorry. So let's, so let M, let M be Z to the N. If I write P under the form sum from M in M of Z to the N, where Z to the A M Z to the N, where Z to the M1, etc. Mn means Z1 to the M1, etc. Zn to the Mn. Then I can write tropicalization of P to be the sum for M in M of AM tropical multiplication. Sorry, X to the M. So here it's a power in the tropical world. And so I can define the zero locus, the dot of P, where it's a locus of points where the monomers reach the minimum twice. And so this belongs to the tropical torus, which is by definition T star to the N. And so T star is, so the natural element for the addition is infinity, so this is just R to the N. Okay, so we can do the same thing for ideal. And so I can tropicalize, I do not, so I can tropicalize, as Eric said, I can tropicalize the varieties of the torus into Rn, which is that just a tropical torus.
Of AMs? No?
Sorry?
In the tropicalization of B, are you taking tropicalizations of coefficients?
Yes, sorry. All right. B of AM. Sorry. Okay, so if I take K, if I take K to be the put of Puiseux series, so I can find things which are interesting, like.
Sure. May I ask a question?
Yeah.
About the tropicalization of the polynomial. It's like I remember like we know the valuation of the zero is actually infinity, right? But what if we break up like break up zero to like 1 plus -1? Oh, well, that shouldn't be a problem. Yeah, thank you. Sorry. Yeah.
Yeah. Okay. So that's interesting what you say. So. Yes, but we start from the torus, so it's okay. I mean, Z1 is different from 0, so you have no problem. I think it's the answer.
Right. Sorry. Yeah. Thank you.
Okay. So if you take K, which is a non-trivial valuation, you can find things like that. So this is a tropical surface with a polynomial of degree 2. But if you take C, it seems to be, so it's a trivial valuation, so it seems to be not so interesting, but in fact, you can still find some fans. So I think it's this one. It's not this one, but anyway. Up. Okay, so if you have a trivial valuation, you will get a fan. So let me write it. or a trivial valuation. We get a fan. So there is only one vertex. Okay, so today, and in fact, in this lecture, we will mainly talk about tropical fans, the tropical Hodge theory for tropical fans, because it's already quite interesting, and we will only talk a few about the general case of any tropical variety. So let me introduce tropical fans. So Eric already introduced most of the thing I will talk now, but I have a few different notations, so let me write everything. So I write n to be a lattice, and R will be n times R. M will be the dual of n, and MR. So this is a dual, right? From n to z, and MR will be MO times R. So for me, let's sigma be a cone. So I will say for me a cone, it will be rational strictly convex polyidal cone. So here, so sigma is something of the form I from 0 from 1 to k. Vi with Vi, V1, I should write it like that, in n, and sigma contains no line. And then I write so I set and sigma R will be so just sigma times R, so it's a tangent space. And sigma is just n sigma R intersected with n, and R sigma is, so when I write sigma as a subscript, it will be things about the tangent space. When I write sigma as a upper script, it will be the quotient. So here it will be just nr quotiented by n sigma r, and n sigma is just n quotiented by n sigma. And so I write the dimension of sigma. I write it as an absolute value, and it is by definition just the rank of n sigma. And so sigma is, so we say that sigma is simplicial if one can choose the V1, etc., Vk linearly independent. So it means, for instance, if I take something like that, so it's a cone over a square. This is not simplicial, okay? So it's a cone over a simplex. And we say it is unimodular if one can choose the V1 Vk to form a basis of n sigma. So for instance, if you take something like that, and you have the lattice, this is not unimodular. Okay, so union modularity in the context of toric geometry, it's so if the toric variety associated to a tropical fan is smooth if only if every cone of the fan is unimodular. So that's why it's important. So it's more or less smoothness in some way. So we will see another notion of smoothness later, like tomorrow. So I will need this definition later. So this is a dual of sigma, and it is by definition the set of linear form such that for x in sigma, the pairing is positive, is non-negative. So this is the dual of sigma. So here, sigma, the dual of sigma is not always strictly convex. It might contain a line. So for instance, if sigma is that, the dual of sigma is that for the standard pairing. And so a face of sigma is any two of the form sigma intersected with the kernel of L for some L. So just what you think about. For instance, if I have something like that. So this is sigma. I can have this is a face of sigma. This is another face of sigma, etc. And so a rational fan is a set of cones. So sigma. Oh yes, for me, a capital sigma will be a fan, not a polyhedral complex. So it's a set of cones such that if sigma belongs to sigma and tau belongs to is a face of sigma, tau belongs to sigma, and sigma prime and sigma, and then the intersection is a face of sigma and of sigma prime. Okay, so we have seen everything like that, and okay, the support of sigma, I write it like that, and it's just a union of the sigma for sigma and sigma. And I write the origin, the cone of the origin with an underlined 0. So faces of dimension 1 are called rays, and maximal faces are called facets. Okay, so now new notation, but Eric already introduced this. So let sigma be a fan, and tau sigma inside sigma with tau face of sigma. So I write sigma with a tau as a superscript. It will be so it is sigma plus n tau over n tau, which lives inside n tau R. So it's an R everywhere. And then I call the star fan of sigma around tau is sigma tau, which is So if I have this image of 4, for instance, so if I look around this toe here, so you look around and you see the star fan is this thing here. So you will see something like that, right? So if rho is a ray, I write so I write a rho to be the generator, so the unit vector, so it's the generator of rho intersected with n. And so definition. The tropical fan sigma of dimension d is a fan where each facet is of dimension d. So it's pure. And for all face, for each face 2 in sigma with 2 of dimension d minus 1, we have sum of e sigma 2 with sigma maybe I forgot to say that this symbol means that 2 is a face of sigma. Okay, with sigma of dimension d, I ask this to be 0, and so it lives inside n2. Okay, so this is the balancing condition. So for instance, here, I have 2 of codimension 1. And if I look to sigma 2, it's just a tropical line. And so I have the sum of the 3 vectors around the origin, which sums to 0. And you can check that it is the case around each face of codimension 1. So yes, here there is a little difference with Eric. Here, in fact, I consider fan here. I consider reduced tropical fan, so I don't put any weight. It will be 0. Just, okay, you can work with weights if you want, but so all weights equals 1. Okay, so I think for now, is there any question? There is nothing new. So so classical Hodge theory, at least at the beginning, works with complex projective compact, so compact projective complex varieties. So here we want to have compact tropical varieties, but a fan is not compact. So we want to compactify it. And so I will introduce what we call canonical compactification of fan. And so the idea is to compactify a variety in the complex torus, for instance. You can use toric geometry, and you can use a take a fan, take the toric variety associated to it, and then take the closure of the subvariety of the torus. So here it's the same idea. So what we want is to have tropical toric geometry. So it's what I will introduce now. So I will try to justify the construction of the canonical compactification, but what is really important is the final description of the canonical compactification of the fan. But let me first introduce tropical toric geometry. So I take sigma a fan in an R, which is just R to the n. And so first you can check that the torus. So let's look at the complex torus, TCN, which is just C star n. In fact, it is isomorphic to the homomorphism of monoids from M to C. The monoid C with a multiplication. Indeed, you can map any Z inside it to the map which map M onto Z to the M, right? So if you prefer this, you can check that this is isomorphic to. Okay, no, let me say it first. So the idea, okay, so it's a little bit different point of view from the definition of toric varieties by Eric, because I need to do it with tropical geometry, and it will be a bit easier to understand tropical geometry with the definition I introduced now. So if sigma is a phase of capital sigma, I can set UC sigma to be the homomorphism from the dual of sigma intersected with n to C star. Okay, so you can see that the torus is included inside this. Okay, if you prefer, you can see that as the C point of the spectrum. So the spect of C square. And it's a C point of that. But okay, anyway, I prefer this. As I explained, I prefer this description. So let me give some examples. So it's the same examples as Eric, but now we will do them again for tropical geometry. So if sigma is just a zero cone, then sigma dual is zero dual, which is just M, the entire M, because any linear form is non-negative and zero. And so we get UC0, it's just a torus. Now, if I get sigma to be, for instance, this thing, the dual is the same. And so UC sigma is the homomorphism from sigma ch intersected with M C star. But you can see that this is isomorphic to C2 because you can just map Z to those things which map M to Z to the M, because M has no non-negative coordinates, no negative coordinates. So you can authorize Z to be 0, and you can do things like that for other fans. And so you can take, so if tau is included in sigma, then you have the inverse inclusion for the dual, and you have an inclusion like that. And so you can define Cp sigma to be the disjunct union of the UC sigma quotiented by the inclusion. Okay. This identifies inclusion. Okay, so now the idea is just to replace everywhere C by T. So first you can check that TTN, which is by definition T star to the N, is isomorphic to the homomorphism of monoid from M to T tropical product. And indeed, this is just, so this is plus. So this is just a homomorphism, linear homomorphism from M to R union infinity. Okay, then it's not linear, it's like, if you prefer, it's over R plus, anyway, okay. And so this is just home from MR to R, because you cannot take the value infinity on M because you have the opposite element. And if you take infinity on some point of M, you must value minus infinity on the opposite. And it's not authorized, so it's just that. So this is just N to the R. And so it is isomorphic to Tn. And so now I define U T sigma to be the homomorphism of monoid from sigma ch intersected with M with T of monoid. But this is just equal to the linear. So, okay, maybe I should be more precise. So it's sigma intersected with M to R union infinity. In fact, here I can just replace M by MR. And here it's, if you prefer, it's over R plus module. So it's a module of smearing. It works like usual module. It's not a problem. So let me give some examples. So as before, if I take sigma to be 0, I get UT0 to be the torus over T. And now what happens if I take sigma to be this? So once again, I have sigma ch to be this. And so I have to take a linear form, which value something on each point here. So I can just take the two unit vectors here and take any element in R union infinity for this, and any element in R union infinity for this. And it defines me an element of UT sigma. So here, UT sigma, it just you can take any value. So it's equals to T square if you want. Okay, so it's a affine plane. So let's take the last example. So I take just array like that. The dual is something like that. And in this case, for this point, I can take any value in R union infinity. But for this point, if I take infinity, then I should have minus infinity here. So it's not possible. So I have to take anything in R. So it will look like this. So I can compactify only on the right. Okay, so to really understand, I think it's like for Toy geometry, you have to make some computation. So if you want, you can try to show that. 20. So on the right, on the left, so you have what is called the projective fan. On the right, there is a representation. So this is the projective fan. On the right, you have a representation of the RP2, the real projective plane. And so you can try to see why this is the tropical projective plane with this definition. So yes, if you have sigma as before, you can define TP sigma to be the union of UT sigma for sigma and sigma, quotiented by the inclusion. And so you can check that if sigma is this, then this is TP sigma. And so you have a correspondence between the faces and the stratum. So I can define okay, I will define.
So if your fan is complete, this thing glued from U T sigmas, will it be compact?
Yeah, yes, exactly. So completeness for this is exactly compactness for this.
But in general, if your fan is not complete, then you might get something non-compact, just like in this example.
So here everything is compact. In this example, this is complete. The triangle is compact, and here it's a representation of RP2. So this point is the same as this point. So it is compact, right? But in general, if this is not complete, I will have something which is not compact. But the idea you will see is that even if the toric variety is not compact, the compactification, I mean the closure of the subvariety will be compact. And it's the subvariety which interests us. So for the stratum, for the strata, I define TP sigma of sigma to be UT sigma deprived from the union of the UT tau or tau a subphase of sigma. So for instance, here it's just this line. Here it's just this point, etc. Okay. And so here you have the correspondence. The origin corresponds to the torus. The red line corresponds to this line at infinity, etc. Okay, so now we have an interesting theorem. So if V is a subvariety of TCN, sigma of fan in an R, then the closure of V inside CP sigma is compact if and only if the support of sigma is included inside the tropicalization of V. And we have exactly the same thing in the tropical world. If delta is a fan, or if you prefer a tropical fan, in NR, then the closure of delta inside TP sigma is compact if and only if the support of, sorry, I think I wrote, of course, it's the other direction. So okay, if sigma is complete, of course, the closure will be compact. And so here it will be the same. So if the support of delta is included in the support of sigma. Okay, and this slide, now we have a canonical way to compactify a fan. And so this is the definition. The canonical compactification of a fan sigma in NR denoted, so we write it over line sigma, is by definition the closure of sigma inside TP sigma. Okay, if you prefer, it's the support of this, but we will see that there is a structure of faces on this. So let's try to understand what is this canonical compactification. So if I take sigma inside sigma, so I define overline sigma to be the closure of sigma inside TP sigma. And I wonder what is overline sigma. So I know that UT sigma is by definition the homomorphism from sigma Chech to R union infinity. And so I have sigma which is included in that. But sigma is also the dual of sigma. So it is the homomorphism from sigma Chech to R plus. And so I want to take the closure of this inside this. And so you can see that the closure of sigma inside UT sigma is just the homomorphism from sigma Chech to R plus. So R plus is union infinity, which is compact. As it is compact, it is exactly overline sigma. Okay, so if sigma is simplicial, for example, I can take sigma something like that. Yes, let me write also this. So it's homomorphism of R plus module. So I can also write this as sigma O times over R plus. So it's the same thing, okay, because sigma dual is the dual of sigma. We can check this, it's not hard. So this is sigma. And I wonder what happens when I take the tensor product with this. So for instance, if I take this point, okay, I can multiply by a positive real number, or I can multiply by infinity, and then I will get some point here. If I take this, I will get a point at infinity here. Now I can take this time infinity plus this. So I will get some point here at infinity. or I can take any other point here. So I will have the whole line here. And I will have the same thing here. And at the end, I will have infinity times this plus infinity times this here. So what happens is that I am replacing by sigma by overlying sigma, which is isomorphic to, okay, maybe I can write it like that. It's be shorter. The dimension of sigma. So I replace a cone by a hypercube. Okay. So now I define infinity sigma to be x times infinity for any x in the interior of sigma. So it's this point. And so if this is sigma and this is tau, I will denote this space by sigma over tau infinity. So by definition, sigma over 2, sigma tau infinity is by definition infinity tau, so this point, plus sigma. And I also can take the closure. And I can define also infinity to sigma infinity to be the fan, which is the union of sigma to infinity for sigma greater than 2. So maybe I should write eta. And so it happens that sigma is just the union of infinity to infinity. That this live inside inside TP sigma tau, and it happens that this is isomorphic to just sigma tau, the star fan, which lives inside n tau. So if I define this to be n tau infinity, I have also the inclusion of this like that. Okay, so let me and so last thing, the sigma tau infinity 1 from the phase structure on sigma tau, sigma compactification of sigma. So it will be more clear with some pictures. So compactification. So on the left, you have a fan. And then you can see the tropical compactification of the fan. So here the hypercube are a little bit slanted, different. So here, for instance, if you had sigma here and tau here, here you had sigma tau infinity. And so on the right, you can see sigma, a bit of TP sigma. So for instance, this red thing is sigma tau, is n tau. And this fan here is sigma to infinity, n to infinity. Okay, so you have really a decomposition of sigma into phases, into the sigma to infinity, etc., or into stratum, into strata, which are the sigma to infinity. Is that clear, this construction? So we will work with it later. So with every phases for so each time you have a tau, which is a subphase of sigma. So now I want to state what I said at the beginning. So I will talk about complement of hyperplane arrangement. So you work into C to the n, and inside it you take some linear form, no, sorry, C to the k, and you take some linear form L1, Ln inside the dual. And so you can write A tilde to be C to the k deprived from the kernel of the linear forms. Start from 0. And now you can just embed this complement of hyperplane arrangement into the torus, CC to the n plus 1, by mapping Z to L0, Z, etc., Ln, Z. And you can quotient on both parts by C star. So the torus quotiented by C star is also isomorphic to the torus, but of dimension 1 less. And so I define this to be A. Now you can also take the tropicalization of A, which lives inside the torus, tropical torus T to the n. So it happens that so for instance, if you take k equals 3 and you take L0, L, so you take also n equals 3, example, and if you take L0, etc., L3 generic, then what you find is this drop of A. So it's a support of this one on the left. You can do the computation. In fact, there is only one equation. So A is defined by Z0. Okay, no, it will be too complicated to explain. So the tropicalization is called a Bergman fan. Oh, it's a support, a Bergman support. And it happens that there is a canonical fan, which is called fine subdivision on tropicization of A, called Bergman fan. So this is the Bergman fan actually, with the subdivision of the faces. So now if you have a fan, you can define the choring of the fan. So sorry, I take simplicial unimodular fan. So let sigma be a simplicial unimodular fan. So the choring of sigma is, by definition, so it is well, it depends on which okay, so we will work with integer coefficient, for instance, or wait, no, I will work with rational coefficients. It will be better. So it's Q. So the variables are indexed by the arrays, and we quotient by two ideals, I1 plus I2, where I1 is by definition the product or of XF. So it's the ideal generated by the XF for F a subset of ray. Sorry, wait, I need to. So it's the product of X row 1, etc. X row K if row 1, etc. row K are not the rays of a face of sigma. Maybe I should go to the right. And I2 is the set of the sum of so it's M in M times Q of X. Okay, so anyway, we have a theorem. Wait, so first, so we have several theorems. So first, A sigma is the choring of CP sigma. Second theorem by Fechner and Uzinski. Fechner, Uzinski. If sigma is a Bergman fan, Okay, sorry. Is the Bergman plan of the complement of hyperplane arrangement A, then the drawing of sigma is isomorphic to the cohomology of the compactification of A inside CP sigma. And so now we have a last theorem by Amini and me. So if sigma is for any tropical unimodular fan,
There's a question. Is the Bergman fan always simplicial unimodular?
yes. So the tropical cohomology that we will introduce tomorrow of the canonical compactification of sigma is isomorphic to the drawing of sigma. And so as a corollary, we get that if sigma is a Bergman plan, then we have an isomorphism between the tropical cohomology of sigma and the canonical compactification of the closure of A. So in fact, we generalize a bit this theorem, and with the mid theorem, so still by Amini. So it's not exactly a corollary, it's a bit a small generalization of the corollary. If sigma is a generalized Bergman fan, so by definition, it means that sigma is a unimodular fan of support tropicalization of A. Then the tropical cohomology, the compactification of sigma is isomorphic to the cohomology of the closure of A inside CP sigma. Okay, so really in this case, you see that the canonical compactification has a tropical cohomology, which is the cohomology of a complex variety, even a projective compact complex variety. Okay, so I will finish there, I think. Thanks.
Are there any more questions? Okay, thanks, Matthieu. And tomorrow we have an early start. Amita Mni is giving his first talk at 11.